Okay, isang magandang buhay para sa ating lahat. So we have here the flexural members. We're going to discuss for the flexural members. So we have the structural elements that carries both tension and compression through the depth of section. So we have the different flexural elements. So we have beam, slab, and girder. So for beams, so a flexural members that is designed to both uniform and concentrated loads. So this member can act a primary structural element in the case of a beam, column, frame, or it can be used to support the slabs or joint slabs. So a flexural member with uniform depth that supports area loads over its surface. So the slab is provided with reinforcement to take the flexure either in one direction or in both directions. Joint slab, a rib slab is slab that takes ribs in one or two directions. For girders, structural members that are used in order to support the beams and designed to span between the exerted columns. So walls and girders or girders. So the girder are always considered to be a primary member. So for beams, we have are usually designated names that's been represented of their functions. So we have girder, usually most important beams which are frequently at wide spacing. So it's a major deep beam that often provides support for other beams. So we have joist. It's a light beam that supports a floor. A purling is a roof beam spanning between trusses or rigid frames. For the stringer, is a main longitudinal beam usually supporting bridge decks. For floor beam, is a transverse beam in a bridge deck. For the spandrel, is a beam on the outside perimeter of the building. Girth, a light beam that supports only the lightweight exterior sides of the building. Other terms such as header, trimmer, or rafter is sometimes used, kumbaga, ginagamit siya. So, ito yung mga commonly ginagamit natin. We have WS, WM, CT, and L shapes. Pero kadalasan, we are using the doubly symmetrical shapes, that is W, S, and M sections. Kasi sila ang most efficient. Pero channels have good flexural strength, but poor in lateral strength. And they require horizontal bracing or lateral supports. So T's and angles are suitable only for light load. So pang light load lang sila. So the flexural strength of rolled section can be improved by adding flange plates. So but if the loadings are too heavy or the spans are too long for a standard rolled section, plate girders are built up from plates I, H, or box shapes and any depth. So for shapes, according to the NSCP section 507.1, so plate girders are distinguished from beams or on the basis on the width thickness ratio, that is H over TW or H over thickness of web. So if the width of thickness ratio exceeds 2,547 over square root of FY, the section is treated as plate girders. So otherwise, it's treated as a beam. So regardless whether it's rolled shape or build up. So beams may be loaded in the plane of the web perpendicular to the plane of the web. If the load is in the plane of the web is referred to as bending about the major or strong axis. So that's the value of IX. Should be used. Kumbaga yun ang gagamitin natin. If the load is perpendicular to the plane of the web, if referred to as a bending about the minor or weak, ang gagamitin natin value ay yung IY pala I mean. Okay. For the steel sections are classified as compact, non-compact, and slender elements sections. For sections to qualify as compact, each flanges must be continuously connected to the web, or webs are and the width thickness ratios must not exceed the applicable limits of set forth in NSCP, so as shown below. So still sections that do not qualify as compact are classified non-compact. If the width thickness ratios of any compression elements exceed to non-compact limit, the section is classified as slender element section. For unstiff elements which are supported along one edge parallel to the direction of the compression force, the width B shall be taken as follows. So we have the for flange or I-shaped members, and this B is 1/2 the full nominal width. For the legs of angles, flange channels, and Z's, T's to. T's yan. T's. This is T's. B is full nominal dimension. For plate, B is the distance from the free edge to the first row of the fastener or line of welds. For stems of T's, D is taken as full nominal depth. For stiff element, for example, we have supported along the two edges parallel to the direction of the compression force. The width B shall be taken as follows. So the web or rolled build up or form section H is clear distance between flanges. So the web of roll build up or form section D is the full nominal depth. For the flange or diaphragm plates is build up section. So the width B is the distance between the adjacent line fasteners of lines of welds. For flanges, the rectangular hollow structural section B is the clear distance between the webs less the inside corner radius on each side. So these are the tables. So medyo malabo, pero kadalasan yan ang mga gagamitin natin. So the compact section have width thickness ratio not exceeding limits set forth in the code. So to be compact, the flanges of the beam must be continuous connected to the web. Therefore, a build section of the plate constructed with intermittent welds does not qualify. So in addition, the following equation must be satisfied by a standard rolled shape without flange stiffness. So we have BF over T, TF is less than or equal to 1 over 70 square root of Fy. So for web in flexural compression only, so D over thickness of web, so square root of equals 1680 over square root of Fy. Here, to prevent a buckling, a beam's compression flange must be supported at frequent intervals. So complete lateral support is achieved when a beam is fully encased in concrete of its flange, so welded or bolted along its full length. So in many design, however, lateral support is provided only at regularly spaced intervals. So the actual spacing between joint points of lateral bracing designated as LB. Yan. So makita natin. Ito yung lateral buckling. Yung dati lang makikita mo yan. Okay. So, for the I-shaped members and channels bent about major axis, so we have members with non-compact sections. So we have here LV is equal or less than LC. So except that their flanges are not compact, so exceeding built-up members and members with yield points greater than 448 megapascal. So the allowance bending stress in both tension and compression is FB is equal to 0.66 Fy. So LC is smaller value of 200 VF over square root of Fy and 137,900 over D over AF multiplying for the Fy. For the I-shaped members and channels bent about major axis. So we have the members with compact section. For members with compact section and with length LB is less than or equal to LC, the allowable bending stress in both tension and compression is FB is equal to Fy quantity multiplied the quantity of 0.75 minus 0.000762 multiplied by BF over 2 TF square root of Fy. So ito yung gagamitin natin. For build-up members with LV is less than or equal except that their flanges are non-compact, their webs are compact or non-compact excluding the hybrid. So the yield points, the allowable stress. So ito ang gagamitin natin yon. Ito, yung KC is equal to 4.05 over H over thickness of web, which is raised to 0.46. If H over thickness of web is greater than 70, otherwise use 1 for the KC. For the members with non-compact section not included in the above, so an LV is less than or equal to 200 BF over square root of Fy. The allowable bending stress in both tension and compression is FB is equal to 0.6 of Fy. So member with compact or non-compact section with LV is greater than LC. So allowable bending stress in tension. So members with compact or non-compact section with unbraced length LV is greater than or equal to LC. The allowable bending stress in tension is FB is equal to 0.6 of Fy. So for the allowable bending stress in compression, the allowable bending stress in compression is determined as the larger value of the given equations. So except that the last equation is applicable not only to section with compression flange. So that is solid and approximately regular in cross section and that has an area not less than the tension flange. So when square root of, actually hanggang dito lang yan, nagkamali lang ng pagsulat. So 703,270 of CB over Fy is less than or equal to L over RT, or equal or less than or equal to square root of 3,516,330 CV of over Fy. Ito ha guys, hanggang dito lang yan. Nagkamali lang ng pag-type. For FB, that is a larger of FB in NB3 is less than or equal to 0.6 of Fy. Yan ang gagamitin natin. So for the B1, that is quantity of 2 over 3 minus Fy multiplying L over RT raised to squared all over 10.55 times 10 to the 6 CV of Fy. So or less than or equal to 0.6 of Fy. That's for the FB1. When LRT is greater than the square root of 3,516,330 CV of Fy over Fy, so FB is larger of FB2 and FB3 is greater or equal to 0.6 of Fy. So, ang gagamitin natin value ng FB2 is 1,172,100 CV all over quantity of L over RT raised squared is less than or equal to 0.6 of Fy. So, for channels, the allowable compressive stress is determined by for any value of L over RT. So, FB3 is equal to 82,740 CV over LD over AF is less than or equal to 0.6 of Fy. Where flange width, ayan, thickness of flange, depth, ayan. So, thickness of web, ayan, area, siyempre, multiplied by BF and TF. So, L is equal to LB. So, distance between cross-section, brace against twist, and lateral displacement of the compression flange. RT is the radius of gyration of the section comprising the compression flange plus 1/3 of the compression web area taken about an axis in the plane of the web. So for the moment of gradient multiplier, CV is given as CV is 1.75 plus 1.05 m1 over m2 plus 0.03 multiplying the quantity of m1 over m2 raised squared is less than or equal to 2.3. For the M1 is the smaller, the M2 is larger bending moment at the ends of the unbraced length, where the ratio of the moments of M1 and M2 is positive when M1 and M2 have the same sign, reverse curvature bending. They are negative if their sign are opposite, so that is a single curvature bending, when the bending moment at the any point of the unbraced length is larger than the both ends of the length, so we can use the 1, CB for CB. And for cantilever beams, we use CB is equal to 1. So here, ayan ang ating reverse curvature. Ito naman ang single curvature. Ang kanyang moment. Ayan. So yung moment diagram, so use this one. Signs and values of CB. Okay. So weak axis bending of I-shaped members, solid bars, and rectangular plates. So members with compact sections, if a doubly symmetrical rolled shape is placed such that bending will occur about its weak axis and solid round and square bars and solid rectangular section bent across their weak axis and allowable bending stress is FB is equal to 0.75 of Fy. For members with non-compact section, for non-compact section bent about their weak axis, so the allowable bending stress is FD is equal to 0.6 of Fy. So yun ang gagamitin natin. For doubly symmetrical, I-shape, and H-shape with non-compact flanges bent about their weak axis, so with their flanges continuously connected to the web, so the allowable stress is FB is equal to Fy, multiply the 1.075 minus 0.0019 FBF over 2TF squared of Fy. So, yan ang mga gagamitin natin. Try natin gamitin. So, we have here, ayan, so we have here a beam build up from the following plates. 450 by 20 flanges and 500 by 20 as well. So the plates are, we use the A36 for the Fy, that is 248. So we're looking for the value of the allowable bending strength for length 4, 6, 10, and 16. So yun ang mga gagamitin natin na length. So we have here the Ix. Solving for the Ix, we have the 450, that is 450 multiplying by 540 squared over 12 minus 215 multiplied by 500 is squared over 12. So, solving for the Ix, yung formula ng Ix natin na yung dati-dati pa natin ginagamit ito. Yung matagal na nating formula. So, we have here, that is 1.4 times 10 to the 9 millimeter to the 4th power. Okay. For Sx, Ix over C, so we have C is 540 over 2. So we have here the value of Sx is 5.28 times 10 to the 6th power. So, millimeter cube. Check for the compactness, compression. So, BF over 2 to the F, that is 450 over 2 multiplied by 20. So, pag chinek natin yan, makuha natin is 11.25. For compact elements, 170 over square root of Fy, that is 10.79. So, lumilito mas malaki ang BF natin over 2 to TF. So for non-element, check natin, 250 over square root of Fy, so 15.87. Since 170 is less than Bf, is less than 250 over square root of Fy, so the compression flange is non-compact element. So yun yung gagamitin natin. So according sa ating table, yan ang gagamitin natin. Ayan. Okay, so for the web, D over TW, 550, 540, I mean, over 20 is 27. For the H over TW, so we have here 25. So limiting the value of D over TW for compact element, so we have 1680 over square root of Fy, which is 106.7. For limiting the value of H over TW, it's for non-compact elements, so we have here 126.7. So ayan sa ating mga codes yan. So since D over W is less than of the 1680 of Fy, and then H over TW is less than 1900 Fy. So therefore, the web is a compact element. So nakita natin, di ba? Kasi 27 lang yun. Ito 106, ito 25, ito 126. Okay, for the LC, we have to use that value. So we have here, using that formula, we get the 5,715. For this one, we get the value of 9,267.5. So it governs. Diba? Check natin yung 4 natin. Ang L is 4 meters. So FB, check natin. So we're going to use for the KC. Ayan. Y is 1. So check natin. So we use 1, the value of KC. So we have here. So solving for the FB, makukuha natin value ng FB is 162.44 megapascal. Ayan. Kasi yung H over TW natin ay nakuha natin 25 lang, di ba? Ayan. Mas malaki pa rin 70. So yun ang ginamit natin, 1. Ayan. Okay, next. For the length of 6 meters, so mas malaki pa rin yun kasi compared sa LC. So we have here available bending stress in compression. So the allowable bending stress in compression is determined as larger value of the given equations. So except that the last equation is applicable by this section with compression flange that is solid and approximately rectangular in cross section, and that has an area not less than the tension flange. So square root of 703. So we have here. So check natin mabuti kung ating mapakon yan, ma-prove. So sorry for the area thickness. Ayan. So we have here 10,666.6 for IZ. We have here 151.52 times 10 to the 8 power millimeter to the 4th power. For the RT, square root of Z over A. So we have here the value of RT is 119.35. So yun yung nakuha natin. So next, kinonvert yung yung length ng 6 to 6 meters, 6,000 meters. Naka-millimeters kasi yan. Okay, ay naka-millimeters. Kasi 6 meter. Tapos, i-convert natin sa millimeter. Parang gano'n. Kaya naging 6,000 siya. Kasi lahat ng value natin naka in terms of millimeter. Ayan. Diba? Kaya okay magtataka bakit 6,000 siya. Saan ang galing yun? Kasi 6 meters convert into millimeter, that is 6,000 meters. Millimeters pala, I mean. So, we use this value of CB, that is 1. So we have here value of 53.25 for that, since L over RT is less than the value of this one. So ito gagawin natin, FB3. So using the FB3, ayan, so we will get the value of FB is 229.8 megapascal. It's less than the 148.8 megapascal na nakuha natin kanina. So, we use the FB kasi yan yung mas sufficient na gamitin natin. For the length of 10 meters, so pag-convert natin, that is a 10,000, di ba? 10,000 millimeters, so 83. So, check natin. So, 119. So, lumilitaw na less than. Kasi mas malaki pa rin, di ba? So, FB larger, so we are going to use, ayan, ito. Kasi nakita mo, mas malaki yung ating, yung 119 compared to this value na 83.79. Okay, so, yung FB larger natin, ang gagamit natin, 0.6. So, this will end our lecture. I hope na medyo may nakuha kayo. So, lahat ng ginagamit din na formula, yung mga ginamit pa natin before na ating mga, lalo sa solving for the eye. So, maraming salamat. Ingat kayo palagi. Stay safe and God bless. So, I hope na makikita pa tayo sa susunod na face-to-face. So, let's pray our family and then maraming salamat po sa ating lahat. Ciao!